To introduce the concept of rational functions, which are ratios of polynomials, let's consider the following problem. So suppose that we have a company that produces calculators, and those calculators are called Shark calculators, and the fixed costs to produce them are of $10,000 per week, okay? And the variable costs are of $10 per calculator. So in other words, if you produce only one calculator, you have to spend $10,000 just to run your warehouse, and $10 for that calculator. So that would be just for one calculator, $10,010. Okay, so way too much. Obviously, you want to produce more than one calculator to compensate for your fixed costs. So first of all, we're going to calculate the costs C of x to produce x calculators. So the cost is always comprised of two parts. You've got the fixed costs plus the variable costs. So that's going to be $10 multiplied by the number of calculators produced. So that's 10x. Okay, so we got fixed plus variable costs. So that gives us a linear function, C of x. Now I want to figure out the cost to produce 2,000 calculators. So this is when x is 2,000. So we just replace x by 2,000 in there. So that's going to be 10,000 plus 10 times 2,000, so 20,000. So this is $30,000. So if you don't mind, I'll put my dollar sign at the end here. Same goes here. Of course, it's so those are the costs per week. So these are, you can always assume here it's dollars per week. What are the average costs to produce 2,000 calculators? We want to find an average. How much is the cost for one calculator? Well, so it's not 10 because you have to incorporate into that cost the fixed costs. So what we do is we take the cost for producing 2,000 calculators and we divide that by the number of calculators produced, so by 2,000. So we take the number we have calculated previously, 30,000, divide that by 2,000, so you get 15, and that's $15 per calculator. So this often is called C bar of 2,000, okay? So the bar is often used in mathematics for something that represents the average. So C bar would be the function that represents the average cost. So we're going to see a general formula for C bar, but just notice that we've calculated C bar when x is 2,000. What's the average cost to produce 3,000 calculators? So that would be C bar of 3,000. So that's similar to what we did before. You calculate the cost for producing 3,000 calculators, divide that by those 3,000 calculators, you get 40,000 for your costs divided by 3,000 calculators. So overall, that's going to be $13.33. So $13.33 approximately. So this is dollars per calculator. What's the average cost C bar of x? So this is where we want to figure out a general formula for average cost. So this is according to what we have written down so far. So look at the pattern here and here. Okay, it shouldn't be a surprise that C bar of x is your cost for producing x calculators divided by the total number of calculators produced. So it's C of x over x. So we want to find a formula for that. So C of x is 10,000 plus 10x. So this was calculated in part A. We divide that by x. So we could leave it like that. We could also write it and so that we divide each term by x. So this is 10,000 divided by x plus 10x over x. So that's 10. So this is again dollars per calculator. So it's a function. If we look at that function here, it's a function that's a ratio of polynomials. So that's why it's called a rational function. Okay. What's the domain of C bar? So here I want the domain in the context of the problem. So we're producing calculators. So x obviously cannot be negative. Okay. On the other hand, I realize you cannot produce 1.5 calculators, but we'll just assume here, okay, that we're looking at values of x that are real, okay. So I'll actually include like fractional x values, but all I want to do is remove some of the the negative values of x, because those are definitely not possible here. So I'll just write that here. Domain is going to be everything above 0. Okay, even though some values there are realistically not possible, like fractional values. But at least because eventually I want to graph C bar, okay, in G, and I'm just going to graph it for the part that I want to focus on, which are positive values of x. So graph C bar of x. So for that, maybe it's easier. We can look at two things, like either the formula I framed here, this one, or we can look at this one and see which one we find is easiest to graph. And I find actually here that the second one is easiest to graph, because it looks a lot like a transformation of the function 1 over x. So here, if you don't mind, actually I'm going to erase this because we're going to need more space. So I'm going to use C bar of x written in the form 1000 over x plus 10. Okay, now how is that? Okay, this is a question for you, so pause the video for a second after I've asked a question and try to answer it. How is that a transformation of the toolkit function 1 over x? So there are two things here. There's the 10,000, this is actually 10,000, not 1,000. 10,000 will, if you've got the function y equals 1 over x, and then you replace 1 by 10,000, essentially you've multiplied everything by, well, you've multiplied your function. That's called as f of x. Okay, this is actually 10,000 times f of x. So we've seen that if you multiply a function by a constant, you're stretching out the values of y, okay, vertically by that factor. So this is vertical stretch of a magnitude of 10,000. Plus 10 is adding 10 to every single y value. So after stretching, you're going to shift 10 units up. So this is how that's a transformation of 1 over x. So maybe starting with 1 over x, okay, this is our toolkit function, but remember now, I don't care so much about negative values of x because of the domain I wrote up there, so the domain for C bar. So I'm just going to graph for positive values of x, 1 over x. Then we're going to stretch everything. If we stretch everything, everything becomes 10,000 higher, okay? But if we're close to 0 here, eventually we're going to get close to 0 again, okay? If you multiply a small number, even by 10,000, eventually it's still going to be small. So it's just going to look pretty much the same way, except that it goes higher faster. So this is just 1 over, 10,000 over x. And finally, plus 10 will shift everything. So notice that how we've got two asymptotes here for our function. The x and the y-axis are asymptotes. In other words, the function is getting really close to those two lines. Now, if we shift everything up, the y-axis will still remain an asymptote, but the x-axis will be shifted 10 up. So, in other words, we're going to have a new horizontal asymptote, which is y equals 10. And in that case, our function will look like this. Okay, so this is y equals c bar of x. So you can see that as here, as when x goes to infinity, what happens to our average cost? The average cost will eventually, c bar of x actually, c bar of x will tend towards its asymptote. Okay, so the y values will actually tend towards 10. Okay, so in other words, as if you produce a lot of calculators, your fixed costs won't actually influence that much the average cost of your calculators, but you have to produce a lot. Okay, we saw that if you produce 3,000, it still shows, right? It's not that close to 10, but eventually it's decreasing. So we can say from going from 2,000 to 3,000, so increasing x, we went down from 15 to 13.33. The idea is that if we increase x a little more, we're going to be able to get as close as we want to the value, an average value of 10. Okay, so this is why we call this this thing here. We can get as close as we want to it. This is horizontal asymptote. There we go. And maybe I should add also that here, so the y-axis, which is also the same thing as x equals 0, this is a vertical asymptote. So a vertical asymptote is typically a vertical line that's such that when the x values of your function get close to it, the y values tend towards infinity. So there's many ways you can have a vertical asymptote. You can have a function that just goes like that, but it could go to infinity on both sides of the asymptote. Of course, it could also go to positive infinity here, negative infinity on that side. So all of these are possible for your vertical asymptote. So those are the features we're going to see for our rational functions. We're going to see that sometimes in the end, when x goes to plus or minus infinity, they tend to get close to a horizontal line. So you've got, in that case, a horizontal asymptote. But for some x values, the function also tends to go towards infinity as they get close to those x values, and those are called vertical asymptotes. Okay, so a typical case of this is the function 1 over x. You also have the function 1 over x squared. If you remember, that looks like this. Okay, which is also, this is also a rational function, since, as you can see, it's a ratio of polynomials. So those are the two typical rational functions we're going to focus on, and we're going to look at modifications of those.